Okay. Today I will discuss the third section of first chapter. Okay, so it's about kernels of a matrix, the rank of a matrix, as well as homogeneous equations. Okay, so we consider an example first. So we consider a consistent linear system AX equal to B. Okay. Whose augmented matrix has a reduced row echelon form. Okay, so let's say okay. As we know from last section, this linear system to be consistent, if and only if that the last column cannot have any pivot. So you can see that the entries here corresponding to the all 0 rows in the coefficient matrix should be 0. Okay, should be 0. Okay, and so this is U. And we know that the solution set of the original linear system would be the same as the solution set of this linear system in reduced row echelon form. So it's equal to here. So which is the set of solutions all right, of 0, 1, okay. So of this, so So this is the augmented matrix of this linear system here. Okay, so we have that. Now, with the pivot, so this we can solve. This is linear system immediately. Okay, so for the first one, for the first row, we have x2 minus x3 plus 3x5 is equal to minus 2, and x4 minus 2x5 equal to 1. So that we can solve. Now, from here, we can express 2 as x3 minus 3x5 minus 2, and x4 is equal to 2x5 plus 1. Now, these two equations do not involve x1, right? So that means that x1 can be freely assigned, right? So you can give x1 any value without affecting the validity of these two equations. All right, now we may make a decision okay, so we make a decision that both x3 and x5 are set to be free. Okay? So we set x3 and x5 to be free. But once we set the x3 and x5, then x2 and x4 will be determined. Okay? Because when we express x2, x4 in this way, we are saying that x2 will be dependent on x3 and x5. So with this decision, x2 and x4 will be determined. Once an assignment to x3 and x5 is done. All right, so this is one decision. Okay. But we may make another decision. That both x2 and x4 are set to be free. Okay? Now with this new decision, then so we will set x3 and x4 to be free. Then we will see that so we want x2, x4 to be free, so that x5 is equal to 1/2 of x4 minus 1/2, and the x3 becomes to x3 becomes to x2. You move there, so plus 3x5 plus 2, which is equal to x2 plus 3/2 x4 plus 1/2. Okay, so if we decide to set x2 and x4 free, then x3 and x5 cannot be free. They will become dependent of x2 and x4. Okay? So that x3 and x5 are determined. Once an assignment to x2 and x4 is done. Okay, so we can select the first choice is we set x3 and x5 free, and then x2 and x4 will be dependent on x3 and x5. Or we may set x2 and x4 free, and in this case x3 and x5 will become to be dependent on x2 and x4. Okay. There are other combinations. For example, you can set x2 and x3 free. Okay? So the other choice, if you would like to set x2 and x3 free, then you are able to express x4 and x5 in terms of x2 and x3. Okay? So you can think about x5 is equal to okay, and x4 becomes to okay. So if you set x2 and x3 free, then once you assign an assignment for x2 and x3, then x4 and x5 will be determined. Okay. So then you have a different possible choices to set 2 of the 4 variables, unknown variable, to be free. Any questions? Okay, now taking the first decision. Any solution in SAB is of the form all right, so x1 can be freely assigned, okay, because that the system of linear equation does not involve x1. And x2 is x3 minus 3x5 minus 2, and you have x3. x4 is 2x5 plus 1 and x5 here. Because we choose x3 and x5 to be free, okay? So that x1 can be assigned freely, x3 and x5 can be assigned freely. And so this becomes to x1. x1 can be assigned freely. x3 can be assigned freely. And this is 0, 1, 1, 0, 0. x5, 0, minus 3, 0, 2, 1, plus a constant, 0 minus 2, 0, 1, 0. Okay, so once we express this one, which is called the general solution of the original linear system, and has 3 degrees of freedoms. Okay, because you have x1, x2, x3 can be freely assigned. Okay, as you can see. So this shows that the solution set consists of is the span of, so it's a span because now this is the first 3 terms give us a linear combination of the 3 column vectors. Okay, so it's the span of the set of of 3 column vectors plus a particular vectors plus this one. Now, especially when x1, x3, x4 are zeros, when they are zeros, then this vector is a solution of the linear system, Ax equal to b. So this one is called a particular solution of the linear system. So this one is called a particular be here. The terminology resemble to the solutions of a linear differential equation. If you learn ordinary differential equation last semester, then you can find a peculiar solution and then a general solution. Okay, so we follow this. Actually, this is the similar situation we have for linear systems here. Okay, so the solution set, all right, consists of a solution of this form. Okay, so if a solution is expressed in this form, we call it the general solution, because that the three coefficients can be assigned freely. Okay, so you have 3 degrees of freedom. Okay, and the last one, this one is called a particular solution. Okay. Of course, you can find other particular solution. Okay, but this is one of them. Okay, so that the solutions set is the span of the 3 vectors plus the particular solution. Okay, so we will examine the meaning of this sum. Okay, we'll examine the meaning of this sum. Okay, so this is just from a simple example here, right? When we solve a linear system, and if the linear system has a reduced row echelon form, like this one, then we can do several different things as to get to the general solution. Okay. Okay, so now this is the observation. This is the observation we observe from this simple example. Now we can extend this observation into a theorem, so it's generic. All right, so let AX equal to B be a consistent linear system. Maybe I will a consistent system of M linear equations with n unknowns. Then they are k pivots in a reduced row echelon form. Of the augmented matrix if and only if. Okay, just like here, there are 2 pivots. There are 2 pivots. So now we have k pivots. If here we have 2 pivots, we find the degree of freedom is 3. What is 3? 3 is 5 minus 2. Okay, because we have 5 columns corresponding to 5 unknowns. And only 2 of the 5 columns have a pivot. Okay. And then in here, the pivot, this pivot corresponding to the second column, so corresponding to the second unknown. This pivot corresponding to the unknown x4. And our first decision is to make x2, x4 to be dependent. Means that x3 and x5 to be free, okay, to be independent. So the statement is that if we have k pivots in a reduced low echelon form of the augmented matrix, if only if they are n minus k free variable, and k dependent variable. In describing the set SAB of solutions of AX equal to B. Okay, so the theorem generalized our observation in this simple example. Okay? So the proof should follow the idea we just examined here. All right, so let U and C be a reduced row echelon form of the augmented matrix AB with k pivots, right? So this augmented matrix has k pivots. Okay, so this is what we know. Now, the forward part. The forward part says that we have k pivots, right, in the row reduced form, and this will imply that they are. We can set a minus k unknown variable to be free, and then the rest k variable to be dependent. Okay, now since the linear system AX equal to B is consistent, okay? Because this is consistent, this k pivot must be in U by theorem 1.2.5. Okay, we discussed the last Wednesday. Okay. Because when it's consistent, if there is 0 rows, the corresponding entry should be 0. So that the last column cannot have any pivot. Okay. Otherwise, the linear system becomes too inconsistent. Okay. So must all in U. Okay, so we let I1, I2 up to Ik be the indices of columns having a pivot. Okay, so now, so for this example, the index I1 is 2, I2 is 4. Okay, I1 is 2, I2 is 4. All right, now since pivots in U have no, so pivots in U have no non-zero entries above or below them, right? Because for this one, all the entry below this pivot should be 0. And for this pivot, all entries up, above, or below should be 0. Okay, they should be 0. So have no non-zero entries up or below them. All right? So each of the unknown variables xi1, xi2, up to xik. So the x2, when we multiply, then because this is 0, right? So the x4 is not in the relation here. So to see here, x4 will not appear here. Okay? On the other hand, for the x4, x2 will not appear in the expression. So each of the unknown variables can be expressed as a linear combination of the raised n minus k unknown variables xj, and j is not equal to I1, I2 up to Ik. Plus a constant. Okay, so just like here, for x2, so now these two unknown variables corresponding to pivot columns with a pivot. And so when we multiply the first, so use the row containing this pivot, you can see that the corresponding unknown variable can be expressed by the raised n minus k unknown variables. So it can be replaced by x1, x3, and x5. 3 and 5. x1, okay. Plus a constant. Similarly for x4, okay? Because you have 0 here, you have 0 there, 0, 0 there. Okay. Okay, so every corresponding unknown variables to columns with pivots can be expressed as a linear combination of the raised n minus 1 unknown variables. Okay. So it can be seen from this particular example here. Any questions? All right, so thus we can set the n minus k unknown variables to be free. Okay, so our decision is to set the raised n minus k unknown variables to be free. And then the k unknown variable xi1, xi2, xik become dependent. Okay. All right. So we proved this forward direction. So once we have k pivots in a reduced echelon form, then they are n minus k free variable and k dependent variable. Okay. In describing the solution set as here. Okay. So this is the forward direction. The backward direction. Suppose that they are n minus k free variables and k dependent variable. Now we will prove the backward direction by contradiction. Okay. So, or well, not necessary. We just let L be the number of pivots in the reduced echelon form. All right. So by the proof in the forward direction part, so they are n minus L free variables and L dependent variables in describing the solution set. Okay, but we know that to describing the solution set, we have n minus k free variables, so that which shows that L must be equal to k, and then we have done. Okay. Okay, so the theorem, so the theorem is just a generic description of what we have observed in this example. Okay. Any questions? So the number of pivots give us the number of dependent variables. Okay, and the other variable can be said to be free. Okay. So once again, you can see that a reduced low echelon form of a linear system give a lot of information. Okay, this is one of them. Okay, with the number of pivots in a reduced low echelon form, we can quantitatively describe the solution set of the original linear system, and to say that the degree of freedom will be n minus the k. Okay. Okay. Now we give a definition. A linear system of the form AX equal to 0. So the right-hand side vector is 0. Then such a linear system is called a homogeneous linear system. Okay, a short remark is that every linear system AS equal to B has a corresponding homogeneous linear system. Okay. And we will see that every linear system is cross-related to the corresponding homogeneous linear system. Okay. Okay, so we let V be a particular solution of a consistent linear system AX equal to B, i.e. AV equal to B. It's very important to put consistent here. Why? Because if the linear system is inconsistent, there is no solution. Okay, so you cannot say let V be a particular solution. No, this is meaningless. Okay, so that to be meaningful, we have to refer to a consistent linear system. All right, so suppose V is a particular solution. Now let U be an arbitrary solution of AX equal to B, okay, which is consistent. Then we have, let's see here, A multiplies U minus U V. All right, so we take the difference to be, so we take the difference between u and v. And we find that this is au minus av, and this is b minus v, and this is 0. Okay, so we show that if u is in the solution set of ax equal to b, then this implies that u minus v is in the corresponding homogeneous linear system, A0 here. Okay, so we know that. Conversely, if u is a vector such that u minus v is in the solution set of the homogeneous linear system, then A u minus AV which is 0 because the difference is in the solution set of the homogeneous linear system. Okay. All right. So this implies AU is equal to AV, which is B. Because V is a particular solution, right? So AV equal to B. So this implies that U is in the solution set. Okay? So if U is a vector such that the difference is in the solution set of the homogeneous linear system, then U is in here. So we conclude that U is in SAB if and only if U minus V is in SA0. Okay, so if and only if U is equal to V plus W with W is in SA0, okay, so U is a solution of the original linear system. If and only if U is equal to a particular solution plus a solution for the homogeneous linear system. So this one proves the following theorem. Okay, so let me state a theorem here. 1.3.4 in the textbook. The solution set SAB of a consistent linear system equal to B is the solution set SA0 of the corresponding homogeneous linear system Ax equal to 0 plus a particular solution of Ax equal to B. Okay, so that is the if we go back to see here the case, we will see that this is the solution set of our inhomogeneous linear system, Ax equal to B. So it's consists of two parts. So you will see that this part should be the solution set of the corresponding homogeneous linear system. Because by the theorem, you know that the solution set SAB is equal to the solution set SA0 plus a particular solution. Okay, so we will see that and give a definition for this set. Okay, so let's take a break up to 11:10. Okay. So we will give a name for the solution set of a homogeneous linear system. Okay, will be called the kernel of A over the null space of A. Okay, so denoted as kernel of A over null of A. I would like to give a remark. Since A0 equal to 0, so 0 is a solution of AX equal to 0. Okay. And the linear system AX equal to 0 is consistent. Right, so any homogeneous linear system must be consistent. Okay, because 0 is the solution. All right, so we immediately have a theorem, 1.3.b. So a consistent linear system AX equal to B has a unique solution if only if the kernel of A is trivial. The kernel of A is equal to, consists only the 0 vector. It's a direct consequence of theorem 1.3.4. You know, for any consistent linear system, the solution set, all right, is the solution, is the kernel of A plus a particular solution. Okay. Now, so if the kernel of A has non-zero solution, I mean that, because 0 is always a solution of the homogeneous linear system. So if we have another solution there, okay, then the number, you see that we have at least 2 solutions for AX plus equal to B. So if you want to have a proof, okay, here is the way to show it. All right? So suppose, all right, suppose the kernel of A is not equal to 0. Okay? Suppose. We use contradiction, right? Or you use counterpositive. The direction is to say a statement P implies Q. Okay? P implies Q is equivalent to not Q implies not P. Okay? You just prove in the first quiz, right? They have the same truth table. So logically, they are identical, right? So to show this one is the same as show this one. Okay. So now suppose kernel A is not equal to 0, the singleton here. That means negative, not Q. Okay, because Q is this one. This is P. This is P, and this is Q. Okay, and then we want to show P implies Q. It's equivalent to showing not Q implies not P. Now, so we suppose not Q. We suppose kernel A not equal to Q. There exists a vector V in the kernel of A, and V not equal to 0. Now, since AX equal to B is consistent, it has a particular solution. Say U. Okay? Then both U plus 0 and U plus V are solutions of AX equal to B. Because of the theorem. If we add up a particular solution with a solution in the kernel of A, then you have a solution for the original linear system AX equal to B. Okay, so both are solution. Okay, but it's a contradiction. Okay. So that's both, and which implies that AX equal to B the solution is not unique. Okay, so it's not P, right? So you suppose not Q. You implies that not P. Okay, so not Q implies not P is equivalent to P implies Q. The backward direction. The backward direction is more directly. Okay, since AX equal to B is consistent, okay, it has a particular solution. Say U. Then the solution set, okay, is the kernel of A plus U by theorem 1.3.4 there. Okay. So you have that. And this is, okay, so this is equal to U only. So the solution set, so which shows that AX equal to B has a unique solution. Okay. Right. So a consistent linear system has a unique solution if and only if the kernel of A is trivial. Trivial means that it consists of only zero vectors. Questions? All right. We need a theorem. If A and B are row equivalent, then kernel A is equal to kernel B. Okay. Okay. Proof. A is not equivalent to B if and only if A can be obtained by the sequence of elementary matrices, okay? Okay, each elementary matrix corresponding to an elementary row operations, either replacement or scaling or swap. Okay, so that A can be obtained from B by doing elementary row operations on B. And that corresponding to multiplying elementary matrix from the left. Okay, from the left there. It is clear that 0 is equal to GK, G2, G1, 0. So for 0 vector, when you multiply with this sequence of matrices, you got zeros. All right, so this implies that A 0 is equal to the augmented matrix. Okay? So this implies that the augmented matrix is rho equivalent to this augmented matrix. But this is augmented matrix corresponding to the homogeneous linear equation, linear system, and this corresponding to the homogeneous linear systems. So that the curl of A is equal to, so that they have the same solution set. Okay? By a theorem we proved before, by theorem 1.2.1. Okay? And this is equal to kernel of A. By definition, this is equal to kernel of B. Okay, okay, so if two matrices are rho equivalent to each other, then they have the same kernel. Okay, have the same kernel. Okay, so now we are able to prove a big theorem of this chapter. As we know that given a matrix, then we can use elementary dot operations. Basically, we can apply Gauss-Jordan elimination procedure so that we end up with a matrix in reduced dot echelon form. Okay, so starting from an arbitrary matrix, by using elementary dot operation, we can end up with a matrix in reduced dot echelon form. So we have the existence of a matrix in reduced dot echelon form, rho equivalent to the original matrix A. But we have to solve a question, because every different person will apply different sequences of elementary dot operations, where we end up with the same matrix in reduced dot echelon form. It's because in principle it's possible if different students work on the same matrix, maybe they will end up with different matrix in reduced dot echelon form. It is possible, right? But from our experience, I think you already practiced a lot, right? By doing assigned recommended homework as well as some quiz problems. You have the feeling that once I do the advanced rho operator, no matter which way I proceed, we will end up with a unique one. But we have to prove that, right? We got the feeling, and we practiced a lot, and all the observations up to now tell us that the reduced echelon form we obtain will be the same. Okay, so we are going to write down this factor. So every m times n matrix has one and only one reduced row echelon form. Okay, so the proof, we will prove by induction on n here. So we would okay. All right, so first, for n equal to 1, okay, now matrix A okay, so it's a column vector, a spatial case, right? Now, there are two cases. All AIs are 0. Then AX okay, so which is in reduced echelon form already, because it satisfies all the properties required for a matrix in reduced echelon form. At least one AIs are non-zero. Then okay, and so we can do the row operations. So we use the scaling, right, to make the entries of the ith row to be 1. And we use the swap okay, and we do replacement. Okay, so we can multiply everyone to cancel them. So we get 1, 0, 0. Right? So starting with an arbitrary m by 1 matrix, we have two cases to see. One is all 0, so the original matrix is already in reduced echelon form. And if at least one component is non-zero, say AI, then we end up with which is in reduced row echelon form. Okay? Okay, so any m by 1 matrix either goes to all zeros or goes to 1, 0, 0, 0. Okay. Okay, so go there. Okay, and also this implies that A cannot to all 0. Why? Why? Otherwise, A because if A and the 0 vector are row equivalent, then A can be obtained by applying row operations, right? And this should be 0, a contradiction. Because we say at least the one AI is non-zero. Okay, so A cannot go through there. So there are only 2 possible. So starting from a matrix A, the m by 1 matrix A, either goes to all 0 or goes to this vector. This is actually this is E1. Okay, this is the standard unit vector E1. Yeah, only okay, and the A cannot go to there. Okay. So obviously, the all 0 vector is not row equivalent to 1, 0. Of course. Maybe I would say also okay, and it is clear if you see any m times n matrices, these 2 are the only m times 1 matrix which is in reduced echelon form. Okay. No others. All right, because as we say, if we have other type of matrix, then it will go to all 0 or 1, 0, 0, 0. Okay? So the theorem is true when n equal to 1. Okay? So now, so we establish the theorem when n equal to 1 explicitly. Now there's no way to go. Just here. The only thing can have there. Right? Second step. For n equal to k, we assume that the theorem is true for any m times k matrix Now we go to the induction step. Now for n equal to k plus 1, we let A, B, and M times k plus 1 matrix. Okay? And we have to show that such an A is one and only one reduced to echelon form. But we prove this by contradiction. So we suppose that A has two distinct reduced row echelon form. B and C. Okay? So A, and we decompose A so AK consists of the first k columns of A, and the A sub little a sub k plus 1 is the last column of A, because now the dimension of A is m times k plus 1. So it goes by row operation to a matrix B in reduced row echelon form. So again, this is BK plus 1. And by another way, then it ends up with C, CK, and the CK plus 1. Okay, so we have this. So there are row operations to end up with a matrix in reduced to echelon form. This is another matrix C in reduced to echelon form. And we assume they are distinct, so they are different. B and C are different. Okay, and from this diagram, so we apply row operations so that you can see that BK and the CK are row equivalent to and we let here note that BK and CK are in reduced row echelon form. Okay? Because the whole matrix is in reduced row echelon form, so the submatrix, the first k column, were also in reduced row echelon form. Okay, because that either they are all all 0 rows is in the bottom, and if a row has a pivot, then that because it's in echelon form, so that this is also in echelon form, and all the entries above the pivot has been cancelled, has been eliminated to zeros. Okay, so themselves, so BK and the CK are in reduced to echelon form already. Okay, so this is very important. Okay? Now, since all right, since they are law equivalent, so we know that BK is law equivalent to AK. So, and right? So BK and the CK are law equivalent to AK, and both of them are in reduced law echelon form. So BK and CK are reduced law echelon form of AK, and must be the same by the assumption okay, because we assume the theorem is true for n equal to k. So they have dimension okay, so this is m times k. Okay, so BK and CK are the same. Now since B is not equal to C, right? So this means that B, the last column, must be different. Okay? So compare these two. BK is equal to CK, but these two matrices are distinct. So we conclude that these two column vectors are different. All right. Also, since okay, so A, B, C are similar, are row equivalent to each other. So they have the same kernel. Okay? By theorem 1.3.5, okay? We just proved. Yeah, here. Okay, so they ABC are row equivalent, so they have the same kernel. Okay, so let U U1, U2 up to UK, and UK plus 1. It's U is in the kernel of A. Then we have BU equal to 0 and CU equal to 0. Okay? So they satisfy both linear systems, homogeneous linear systems. And so that B minus C times U equal to 0. So we look at the detail. So so we look at the detail that we have all zeros here. The difference. So when we do the difference between these two matrices, this is cancelled, so they are all 0. And the last column becomes to B1 k plus 1 minus C1 k plus 1, B2 k plus 1 minus C2 k plus 1, BM k plus 1 minus CM k plus 1, and U1, U2 up to U k plus 1 equal to 0, 0. All right, but because the B column and C column are different, so at least the one component is non-zero, right? So since B k plus 1 is not equal to C k plus 1, there exists an I M such that so I think I find an either okay. So there is I such that Bi k plus 1 is not equal to Ci k plus 1. Okay, so the ith row, the last entry of the ith row is non-zero, and when we multiply with this column vector, we find that with Bi k plus 1 minus Ci k plus 1 times with U k plus 1, which is equal to 0. Okay, so a certain Bi k plus 1 minus Ci k plus 1. So this is the multiple with this column. You give put all 0 here, right? So you give the entry, which is equal to 0. 0 here. All right, so this implies that U k plus 1 must be 0. Must be 0 here. Okay, so whenever you have a solution, you have a vector in the kernel of A, the last component should be 0. Okay, should be 0 here. Okay, so that's the last component, U k plus 1 of any solution, U of Ax equal to 0 is 0. Okay, and which implies that the unknown variables xk plus 1 cannot be chosen to be a free variable. Okay? In solving the homogeneous linear system. Okay? So this implies that that's the last column of B and C must have a pivot, i.e. the B of k plus 1 is equal to EI and C k plus 1 is equal to EJ for some M. Okay? Any questions? Because when we they are in reduced row echelon form. And as we know that if the corresponding, so that the last variable, okay, cannot be chosen to be free because that it must be 0. So cannot be chosen to free. If cannot be chosen to free, that means that they must have a pivot. If there is no pivot corresponding to the, okay, because right? So the last column here, this is the first column. The last column, if the last column has no pivot, then as we just discussed previously, that if there is a pivot there, without a pivot, then they can be said to be free. Because every column has a corresponding unknown variable. I'm sorry, every column contains a pivot. The corresponding variable will be dependent. So if we have k pivots, then we will have k dependent unknown variables. And the rest n minus k variable can be stacked to be free. Okay, this is at the beginning of today's lecture, right? And so that, and because the last component should be 0, so it cannot be selected to be free. So that's why this column should have a pivot. Okay, because it become to be dependent. All right, so the last column should be EI or EJ, because B and C are in the reduced Rho-Shaped form. So if a column has a pivot, it must be a standard unit column vector, either EI or EJ. Okay. Okay, so now B becomes to BK EI, and C becomes to CK EJ. With BK equal to CK already. Okay, so we know BK is equal to CK, and EI is EJ. All right? All right, and they are in reduced echelon form. All right, so they are in reduced echelon form. So if this is EI, all the the ith row of BK, the ith row of BK is the uppermost zero row of BK. Because it's reduced echelon form. So if we have EI, because that means that in the ith position we have 1, and then there must be all zeros, because this is in reduced echelon form. All right, so depth to a pivot, the entry must be all zeros, and so the ith row of BK should be the uppermost 0 rows of BK. All right, above I, you must have a pivot. Okay, you must have pivot because of the echelon form. Okay, so that you have I here. It's ith row. Okay, and here is BK. Okay, so that you must have all zeros. They are all zeros. Okay, and you have 1 here, you have 1 here. This is the pivot. So the ith row of BK is the uppermost 0 row. Okay, the uppermost 0 row of BK. This is for this one. And the J's row of CK, similarly, the J's row of CK is the uppermost zero of CK. Okay, from the J's. Right, but BK is equal to CK. So if they have they must have the same uppermost zero because they are the same. So we must have I equal to J. And then BK plus 1 is equal to E equal to CK plus 1 equal to EI. Okay. Right? And which is a contradiction to B not equal to C. Okay, so we get a contradiction finally. Okay, so that's any M times K plus 1 matrix has 1 and only one reduced echelon form. Okay, so by induction on N, any M times N matrix has 1 and only one reduced row echelon form. Okay? Okay, so this is the end of the proof. It's long, but it's elementary because we just use the concept of kernel, and as well as how the solution set can be generated. Okay, and to end up with the proof of the big theorem. Any questions? I'm sorry, I have checked 10 more minutes from you. Okay, so I'll stop here.